We got a couple openings here, and we got a wave. Doesn't matter really whether it's a water wave or a light wave or a sound wave or anything, any kind of wave that's approaching the barrier with the two openings. We know that the wave will go through the two openings there, and it will diffract. It's going to spread out. That's what diffraction is, right? It's the spreading out of a wave like this. Now, the amount of diffraction, well, that's going to be affected by the size of the opening. That's going to be affected by the wavelength, the frequency of the light or of the wave, and so on and so on. We're not going to worry too much about that. Bottom line is, as it spreads out, both of these diffracted waves are going to hit each other. They're going to interfere with each other. And we're going to get areas as a result of that constructive interference and destructive interference. When a crest meets a crest, trough meets a trough, we get constructive interference. When a crest meets a trough, we get destructive interference. So we're going to get these alternating lines of constructive and destructive interference. If these are water waves, then this line right here would be an area of constructive interference, and these water waves would be really big waves. Okay, if you're laying on an air mattress, kind of just trying to get some sun, in the pool or whatever it is that has this interference pattern taking place in it, then you're going to be bobbing up and down pretty good at this point, because you're going to get crests that are twice as high as the crests were, and troughs that are twice as low as the troughs were. So you're going to get big waves that are twice as big. But then right beside it, you're going to get an area of destructive interference, where there's nothing. There's nothing, literally nothing. The waves completely cancel out. So you can be on your air mattress there and experience just a nice, calm, enjoying the sun, not bobbing up and down at all. But then you go over a little bit, and once again, you're going to get this bobbing up and down like crazy again. We have constructive interference. That's on both sides. And then you're going to get this area of destructive interference, and so on and so on and so on. If those are water waves, you're going to observe that, because water waves are particles, and we can see particles. But if it's light waves, we're not going to see this, because light has to reflect off of something in order to be observed. So what we have to do if we're observing the interference of light waves is introduce a screen over here. The screen over here is going to have an interference pattern showing up on it. You're going to get right here a bright spot. That's where you had constructive interference. And then next to it, you're going to get, we call it a dark spot, but it's not like a black spot. It's just the absence of a bright spot. If there's light around, then it's not going to be dark. But it's going to be dark in the sense that you're not going to have the bright spot or any light as a result of this interference. So we'll call it a dark spot. Bright spot, dark spot. And then we get another bright spot where there's constructive interference, and then a dark spot. And then we get another bright spot over here, and so on and so on and so on. Same deal on the other side. Bright spot, dark spot, bright spot, dark spot, and so on and so on and so on. I'm going to erase this now, because although this is actually taking place even with the light waves, we're not going to see it. So we're just going to include in my diagram what we're going to see, which is the interference pattern produced on the screen. Now, we got a couple of equations that describe the interference pattern that's formed here. What I want to do right now is identify, again, the variables that appear in those equations. First one is little d. Where's little d? What does little d represent on this diagram, Brad? Good, the distance between the openings, and that's going to be typically measured in meters. If you want to find the wavelength in meters, then you better make sure that d is in meters. Good, what else? Let's go with L. I make it a capital L, but of course on your equation sheet it's a lowercase l. I just don't want it to look like a 1 when I'm writing it on the board here. What's L represent? Aiden, what's L represent? Good. Distance from the screen to the slits. Excellent. And we got another one, X. All three of these are kind of distances, right? Measured in meters. What's X going to represent there, Riker? Yeah, it's the distance between the node or the antinode or antinode and antinode or node and node or whatever you want. It's the distance between any node and any antinode or any combination of those. So it could be this distance. It could be this distance. It could be this distance. It could be whatever we want. As long as n is consistent with it. What's n going to represent? What's n represent there? Sean, what's n? Not the distance. Yeah, it's the difference. It's the number, right? The difference in the antinode number here. So we're going to say that, well, let's identify this one first as our central maximum or our central bright spot or our central antinode. First order maximum, second order maximum, same deal on the other side. And then let's identify what n would be for each of these three values of x. N for this one would be, yeah, 2, right? 2 minus 0 is 2. N for this one would be, what do you got there? Cassie, what do you got there for this one, n? Good, n is equal to 1 there. Not because this is a value of 1, but because 1 minus 0 is 1. If it was 3 and 1, then it would be 2. If it was 1 and 1 on the other side, then it would also be 2. What about this one? What would n be equal to there? This is the toughest one here so far. Hidden? N would be 1.5 here, because we're going to consider these to be 0.5s, right? 0.5, 1.5, and so on. 2 minus 0.5 would be 1.5. Good. Finally, one more variable, and that's going to be theta. Theta is an angle, of course, right? Okay, I'm not even going to insult you by asking you, hey, what's theta represent? An angle? Yeah, of course it's an angle. Okay, but what angle? It's kind of like x in the sense that it can be multiple values, but it's kind of not like x in the sense that it can't be as many multiple values as x is. Good. It's got to be measured from the central antinode, from the central maximum, from the central bright spot, whatever you want to call it, to whatever other maximum or minimum you want to measure it to. So we can measure it from the central maximum to the second order maximum. We could measure it from the central maximum to the second order minimum. Doesn't matter, whatever we want. Okay, as long as n is consistent with that. In this case, n would be what? Caitlin, what's n going to be in this case? 2. Good. And what's n going to be in this case, Talia? Good. Good. Excellent. Now, these questions tend not to be crazy hard if we remember what each of these variables means, and that's a big if, because it's kind of tricky sometimes to distinguish between d, l, and x, and remembering which one is which, because they're all in meters, right? Wavelength is in meters as well. That's 4 different variables that's measured in meters. Okay, that can get a little bit confusing. If you can keep that stuff straight, keep the units straight, because a lot of times we see centimeters here. A lot of times we even see nanometers here for a wavelength. If we can keep the units straight, and always remember to go to meters. Okay. And finally, if we pay attention to whether we're dealing with nodes or antinodes, bright spots or dark spots, then we can do these questions. Okay. None of them tend to be very difficult if we pay attention to all those things. Rucker? Okay. What if x was measured from the first order node, antinode on one side, to the first order node on the other side, did you say? Okay. Yep. Yep, fair enough. Fair enough. That's a good question. Well, you could measure theta there, because theta has to be measured from the central maximum. I'll talk very, very briefly about what you could do in a second if you had to deal with theta there. Okay, but right now, let's look at what the value of n would be for that. Okay. You tell me, what would the value for n be for that? Good, n would be 1.5 for that. So generally, as long as that little condition, that little rule of thumb that we talked about yesterday is met, then we're just going to use the second equation, which was lambda is equal to xd over n times L. We couldn't use lambda is equal to d sine theta over n, because of course theta has to be measured from the central maximum. Now, could you conceivably use this equation in a situation like that where it's not measured from the central maximum? Yes, but I'm pretty sure you're never going to have to do that. Here's what you would have to do if that situation arose. You would have to look at this as one problem, And then you would have to look at this as another problem, and then you'd have to combine them. Does that make sense? Pretty sure you're not going to have to do that. Pretty sure. Got it? All right, let's take a look at the homework that we had last night then. 3 questions on page 691. Any issues with any of those 3 questions? We're not going to worry so much about, okay, they asked us for the light's color in question number 2, just like that example problem we had. We're not going to worry so much about the color of the light. As long as you recognize it's visible light, that's probably okay. Anything else besides the issue with recognizing that it's red light there? Yep. Number 3. Any others? Okay, number 3 it is. It says a student uses a light with wavelength 5.00 times 10 to the minus 7 meters, which that's not a surprise because that's visible light, and we expect to see visible light in these questions. Found the distance between the third node and the central antinode. Third node and the central antinode. Listen, I like to draw this out. Okay, you don't need to draw out the complete diagram like I did right here, but I think it's useful in a question like this to draw out at least the interference pattern that you see on the screen. At least one side of it. There's my central antinode, my central bright spot right there. This would be my first order antinode, or first order maximum, second order, third order maximum, fourth order maximum, and so on. We're trying to find the distance between the third, or we're given, I should say, the distance between the third node, which is a dark spot, 1, 2, third node, and the central antinode. So right here. Okay, this is going to be x. X is 1.00 times 10 to the minus 1 meters, or 0.100 meters. And what's n going to be corresponding to that there, Dallas? Good. N is going to be 2.5. It is so easy in this question, and this is what we were talking about, right? Got to pay attention to these things. Okay, it's so easy to say n is equal to 3 there, right? You see the third node, central antinode, 3 minus 0 is 3. But we're really looking at 2.5 minus 0. So we got x, we got n, we got lambda, we got L is 1.2 meters. The distance from the screen to the slits. What are we looking for? How far apart are the slits? Looking for D. All right. I think it's pretty clear which equation we want to use here. D sine theta over n, xd over n times L. We want to use this one, but we might have a problem. This equation is only valid. This equation is an approximation all the time. It's never perfect, but at small angles under 10 degrees, it's a good approximation. So we're going to say it's only valid under 10 degrees. What's our rule of thumb to determine whether we have an angle that's less than 10 degrees? Yep. Good. If L is greater than 10 times x. So let's take the value of x and let's multiply it by 10. What do you get when we multiply x by 10? 0.1 times 10 is 1. What's the value of L? 1.20, right? So is L greater than 10 times x? Yeah, not by a lot, actually. Not by a ton. Okay, we'd be dealing with an angle that was bigger than the angles that we were dealing with yesterday here, for sure. Okay, we'd be dealing, yesterday we saw angles that were like 0.08 degrees, right? Here we're dealing with an angle that's significant. It's above 1 degree. Okay, it's probably 4 or 5 degrees. Okay, but it's small enough to allow us to use this equation. X is 0.100 D. Sorry, we're looking for D, aren't we? So we've got to rearrange that equation to solve for D. The NL goes up, the X goes down. Lambda times N times L over X. Lambda is 5 times 10 to the minus 7. N is 2.5. L, 1.20. 0.100. We'll get to D. We solve for D. It works out to be, I assume the answer they have in the book there, 1.50 times 10 to the minus 5 meters. Is that okay? Yep. So question number 2 you're talking about. Yeah, okay. The wording of that's not great, actually. It says the distance between antinodes. What they mean there is the distance between adjacent antinodes, antinodes that are beside each other. Okay, now, they should have said that. That's what they meant, but they should have said that. If it's adjacent antinodes, some people might still look at it and say, well, which antinodes? It doesn't matter. Okay, if it's second, third, if it's the 15th and 16th, it's still n is equal to 1 in that case. But we do need to know that they're right beside each other, for sure. All right, let's say we had looked at this question, okay? Let's say we had looked at question number 3 that Dallas asked me to go over here. And let's say we had went through our little rule of thumb and we found that L wasn't greater than 10 times X. Or let's say you're just not comfortable using this equation. You just say, look, I want to use the one that I know for sure is valid. Lambda is equal to d sine theta over n. Could we do that? Because we're measuring from the central max, okay? Central max is part of the deal here. We can absolutely use that. Let's figure out how we would. Let's erase this stuff, actually. Give me some space here. We know what the value of x is. Okay, we know that this value was, what was it? I erased it. 0.100, right? We know what the value of L is. It's 1.2 meters. Now, this isn't to a very good scale, right? Clearly, this one should be quite a bit smaller than it is compared to this, but good enough. Okay, we want to find that value of theta right there. We would say tan theta is equal to opposite over adjacent, and we'd solve for the value of theta. Somebody figure that out for me right now, okay? We end up getting 4.7 degrees there. Thank you, Hayden. Now that we have that theta, we could absolutely go back and say lambda is equal to d sine theta over n. D, we know what that, sorry, we're solving for d again, right? So we're going to rearrange that. D would be equal to n times lambda over sine theta. So n would be 2.5 times 5 times 10 to the minus 7 over sine 4.7 degrees. What do you get for d there? It's going to be around 1.5 times 10 to the minus 5, maybe slightly different. We get 1.51 times 10 to the minus 5 meters. I've seen this before on a diploma exam where we've had an angle that's been less than 10 degrees, but they key it, in numeric response question, they key it to accept a couple possible answers. Okay, 1.50 and 1.51 would both be acceptable here, okay, if it was a numeric response question. If it was a multiple choice question, you're not going to have two options that are that close. So if you get 1.50 and there's an option that's 1.51 here, pick the 1.51, right? And same deal the other way around. Which is technically a better answer? Right? 1.51, right? Because that's using the equation that's exact, not the approximation. But this would also, I guarantee it, be marked correct as well, as long as that rule of thumb is met, as long as the angle is less than 10 degrees. They'll have it keyed to accept both answers. Okay? They do that fairly often, actually, in different questions when there's a rounding issue or something that could cause a different answer depending upon your method. Okay? But they always make sure that they account for every possible way of solving the question, every valid possible way, that is. All right? Okay, I want to take a look at another example, but this one is going to seem to be a little bit different here. This one says a diffraction grating has 1,000 lines per centimeter. What's a diffraction grating? Well, we used that term yesterday, but we didn't really talk about what it was. Yep. You had slits all over the place. Well, not all over the place, literally, but you got multiple slits, not just two openings, but maybe you got 100 openings. Maybe you got 1,000 or 10,000 openings instead of two. Now, the interference pattern that you see is essentially the same. So it's not going to change things dramatically for us. But again, instead of having this with two openings, you're going to have this with hundreds or even thousands of openings. Now, instead of expressing the distance between these openings, typically with the way we express it this time when we have a diffraction grating is not the distance between the openings, but rather the openings per distance. So kind of the inverse of that, right? Instead of this value right here, the distance per opening, we've got the openings per distance. So when you see a value that's 1,000 lines per centimeter, that's not D. That's not little d, but it's close. That's going to be what? Yep, 1 over D. Do you understand that? If you ever see a diffraction grating and it's got 1,000 lines per centimeter or 1,000 lines per meter or 500 lines per centimeter, it's not D. Okay, it's not D, but it's 1 over D. So we can find D pretty easily there. All right, let's go on to read the rest of the question. When light passes through the diffraction grating, an interference pattern is produced on a screen 4 meters away. That's going to be L. The first order bright fringe is produced 19.2 centimeters away from the central antinode. Okay, so central antinode, first order bright fringe, N is going to be equal to 1 here, right? Okay, and this is going to be X, although remember to circle these things, right? Because we want to deal with those later on. We want to find the wavelength. And again, we're not going to worry about the color so much. We know it's probably going to be 10 to the minus 7 meters, which is visible light. What color visible light? Whatever. Okay, so let's do what we do. Probably want to use lambda is equal to xd over n times L for this. But let's make sure that we're allowed to. Braden, what's the rule of thumb for this? To see if we're allowed to use this equation? Yeah. Is L greater than 10 times x here? Well, the value of x is 19.2 centimeters or 0.192 meters. Multiply that by 10, we're going to get 1.92 meters. Is L greater than 10 times x? Yeah. Yeah, it's about 20 times x, right? So we're allowed to use this equation. Let's do it. Looking for lambda. So we got x is 0.192 meters. D we've got to find. D is going to be 1 over 1,000. So it's going to be 0.001, right? What is it? Good, good. Don't convert this to lines per meter. Don't do that. Get it in centimeters, get D in centimeters, and then convert it to meters. Why am I telling you that? Why am I telling you not to convert it to lines per meter? It's possible to do that. Okay, but I'm telling you don't do it. Yep. It does make things more difficult, and here's why. How do you convert centimeters to meters? Well, we all think it's divide by 100, right? It is. But if it's lines per centimeter to lines per meter, we're actually going to have to multiply by 100 there because centimeters is on the bottom. We can do that, okay, but I think that's confusing. If you got lines per centimeter, then get it in centimeters and then do what you usually do for converting centimeters to meters, divide by 100. So this would be 0.001 times 10 to the minus 2 meters, or just bring it over 2 decimal places. So get the centimeters on the top and then convert it to meters. And we said was 1. Okay, that's good. I'd like to have number 1 on the bottom. And then, of course, L on the bottom is 4. So let's do this one as a group here. We got 0.192 times 0.001 times 10 to the minus 2 divided by 4. 4.8 times 10 to the minus 7. If you get a value for lambda that's 10 to the minus 7, in all likelihood, you've done it right. The only real possible mistake that you could have made is with n. Okay, because if you convert wrong, or you go 1 over D and forget to divide it, forget to flip it over, or you don't convert to meters right here, you're not going to get 10 to the minus 7. The only thing that's going to give you 10 to the minus 7 and be wrong is having a value for n of 1.5 or 2, right? You can get the value of n wrong and still get 10 to the minus 7, but everything else is going to give you a number that's not 10 to the minus 7. Okay? Yep. I don't remember, but I'd have to convert that to frequency, and assuming that if it's up close to that 7.5 times 10 to the 14 hertz range, then yeah, it would be blue or violet. Got it? Okay, I'm going to give you about 5 minutes to work on these 3 questions, please, on page 693. Let's take a look at question number 1. It says an unknown wavelength of light is incident on a diffraction grating of 2,500 lines per centimeter. We know this is 1 over d, not d, 1 over d. Okay, if it was d, then it would be centimeters, not lines per centimeter. So we're gonna circle that as well because we want to make sure we convert that to meters in the end. Distance between the central antinode and the third dark node. Okay, here's the central antinode. First, second, third antinode. There's the, this is our third antinode right there. And that distance x is 20 centimeters. And we know the value of L is 50 centimeters. Looks like with what we have here, we want to use the equation lambda is equal to xd over n times L, but we have an issue with that. We can't do that because L is not greater than 10 times x. If we multiply x by 10, then we're going to get 200. So L is not even close to being greater than 10 times x. So let's figure out what the angle is. Let's say theta is, tan theta is equal to opposite over adjacent, or theta is the inverse tan of opposite over adjacent, 20 over 50. What does that angle work out to be? To an unrounded value there. 21.8 degrees. Anybody else get that? Okay, so we get 21.8 degrees, which now allows us to go back to the equation that always works for us, that's perfectly valid 100% of the time. Lambda is equal to d sine theta over n. We're solving for lambda here, so we're going to say d is, do we know what d is? Oh, we can find d. 1 over d is 2,500. So d is 1 over 2,500. What does that work out to be? 0.4 times 10 to the minus 4 for centimeters, right? Is that right? 4 times 10 to the minus 4 centimeters, which we want to convert that to meters, 4 times 10 to the minus 6 meters. Is that right, Jazzy? Okay. So let's now plug that in here. And we divide that by the value of n, which we're going to see is 2.5 here. And what do we end up getting for lambda? Got it? Yep. Times 10 to the minus 7. Okay. What did you do? Forget to convert up here? Okay. Good? All right.